with the knowledge that we have acquired on the chemistry of alkynes, and that is their reactions with HX, their reactions with X2, their hydration reactions, for example, the mercury catalyzed hydration reactions, and also the hydroboration oxidation to make all kinds of various carbonyl compounds, and then later we learn about the reduction of alkynes to make alkenes, or even the corresponding alkanes. Now, with that in hand or in mind, can we utilize the knowledge in order to make a simple molecule, to make a complicated molecule from a simpler molecule? For example, to go from a simple alkyne, like a terminal alkyne, into a little bit more or relatively more complicated target molecule. So this, if we have this, then this we can describe it as target. In a synthesis, for example, yeah, so this would be described, the end, if you like, the end compound, the end molecule is described as target molecule. And what we start with is the starting compound, okay, the starting molecule. You can call it starting material as well, yeah. So this is the starting material. So if we have this starting material and we wish to transform it into a target molecule. So this transformation could be done in one step, it could be done in 2 steps, or multi-steps. So we need to be able how to achieve this transformation based on the knowledge that we have acquired. So let's now consider the chemistry of alkynes as a theme in this regard. Yeah? Okay, so always when we have a target molecule, there are 2 or 3 points that we have to pay attention to. I would say the first one is the number of carbons, in the target molecule relative to that in the starting compound. Is there an increase in the number of carbons, or a decrease, or the same? If it's the same, then that is simple chemistry. There's no bond formation reaction, there's no cleavage reaction, for example, as ozonolysis or KMNO4-induced cleavage reaction that we have learned. So if the number of carbons has increased, then we should think of the possible reactions by which the number of carbons can increase. And in this case, again, with the theme of the chemistry of alkynes, the one way to increase the number of carbons is by acetylide alkylation. Is, of course, formation of the acetylide ion first, and then acetylide alkylation. So this is one way, in this case, to increase the number of carbons. So the number of carbons could increase. It could also be the same. If it's the same, then obviously there's no way for the acetylide ion formation or alkylation to be part of the steps of the synthesis. That's not possible. If the number of carbons has decreased, then again, this cannot be, the acetylide alkylation cannot be part of the synthesis. If there is decrease, then there could be cleavage reaction. So if there is decrease, then we think of, for example, ozonolysis. That's possible, because this is one way by which the number of carbons is decreased. And ozonolysis is possible. Cleavage using KMNO4, or induced by KMNO4 as a strong oxidant. So these are cleavage reactions here, are possible means, if you like, for the decrease of the number of carbons in a molecule. So this is very important to observe at the beginning before you commit. So whether there is an increase in the number of carbons, the same, the number of carbons has not changed, basically, it remained the same, or if the number of carbons has decreased. So there is an increase, again, with the knowledge of the chemistry of alkynes, then we could think of acetylide alkylation as one way, somewhere in the synthesis, by which the number of carbons has increased. If it's the same, then no, there's no such reaction. If there's decrease, also there's no such reaction. If there is decrease, then we should think of cleavage reactions, such as ozonolysis or KMNO4-induced cleavage reaction. So the number of carbons is very important to note or observe in the target molecule. The other important observation that we should make is the types of the functional groups, the types of functional groups present in the target molecule. So what do we have? We have an alkene here, for example. We had an alkyne before. So there has to be a reduction at some stage in the synthesis. Yeah. So the functional group will tell us, will guide us into achieving a possible synthetic route, if you like, or plan for the transformation that is desired to be achieved. Yeah. So very important, the number of carbons and also the functional groups. If you look at the target molecule now, in this specific example, you will see that there is an increase by 2. So there is an increase by 2 carbons in this target molecule relative to the starting material given, which is the terminal alkyne. So there is an increase in the number of carbons. So therefore, an acetylide alkylation reaction could be one of the steps of this transformation. The other observation is functional groups. If you look carefully at the target molecule, you will see that this is an alkene, and specifically an alkene of trans double bond geometry. So this is a trans alkene, a very important observation to note before you commit again, because this will help you organize the steps in a scientific manner or in a reasonable manner that will allow us to achieve the transformation design. So there is a trans alkene here. There is an increase by the number of carbons, all of the number of carbons by 2. Now trans alkene. So there's only one way now, giving the knowledge again, or the chemistry of alkynes, by which trans alkenes can be produced, and that is from internal alkynes by reduction or by using sodium, for example, an alkali metal in liquid ammonia. So sodium in liquid ammonia, lithium in liquid ammonia, or potassium. So this should be the last step actually, because the formation of the trans alkene. So again, formation of trans alkenes can be achieved by sodium, liquid ammonia, reduction of an internal alkynes. Of course, an internal alkyne of the same number of carbons, where 2 carbons have already been installed. Yeah. Okay. So this will be the terminal alkyne. The position of the carbon-carbon triple bond should be the same as that of the carbon-carbon double bond in the target molecule, and then 2 carbons. So these 2 carbons, the double bond here basically was obtained by reduction of this carbon-carbon triple bond, and then we have the isopropyl unit here. So this is a reduction of this internal alkyne into the trans alkene, utilizing or using conditions such as sodium in liquid ammonia. This approach is called backward approach, by the way, or backward thinking, if you like, in synthetic planning. Yeah, it's very important to think of this backward rather than starting from here. So always start from the product, analyze it based on the number of carbons in it, and also the types of functional groups present, and then you take it backwards step by step to see how can you achieve the trans alkene, for example, or the functional group from a simpler molecule or simpler intermediate product that could be part of the synthesis. Now this is an internal alkyne, and we know that we can make internal alkynes from terminal alkynes by reacting the terminal alkyne with a suitable base such as sodium amide, and then elongate the chain by the number of carbons that increase the chain. 2 carbons, the chain has increased by 2 carbons. So we need therefore an alkyl source of 2 carbons, basically an alkyl halide that has 2 carbons. So the conditions therefore would be to take the terminal alkyne to the internal alkyne in 2 steps. Step 1 will be the formation of the acetylide using sodium amide as a base. And then step 2 would be an alkyl halide that has the difference in the number of carbons. So the difference here is 2. So we need an alkyl halide with 2 carbons. So it could be one iodo, for example, ethane, it could be one bromoethane, it could be one chloroethane, 2 carbons here. That's because 2 carbons are needed, or the number of carbons should be increased by 2. That's exactly why an ethyl halide is used, or alkyl halide with 2 carbons is used. So the synthesis now in the forward sense would be to take the terminal alkyne into the internal alkyne by 2 steps, a 2-step reaction. The first step is deprotonation using sodium amide. The second step is alkylation of the acetylide by a suitable alkyl halide, and then the internal alkyne will be reduced so that a transalkene is produced, and the only way to make transalkenes from internal alkynes is to use an alkali metal in liquid ammonia method. So this is how this transformation can be achieved. This is another example of an organic synthetic question. Basically, a synthetic transformation that takes this starting compound into that target molecule. Okay, so we have now this alkene, and we have an alkane as a target product. And as we discussed before, we need to pay attention to 2 observations in general: the number of carbons in the target molecule, and also the functional groups present. And if you look at the number of carbons in the alkene, okay, so if you look at the number of carbons, and if you number them just to keep track of carbons, you will see that there are 5 carbons. So these 5 carbons are probably these 5 carbons. So you can put the numbers tentatively, at least for now. So 1, 2, 3, 4, 5. So these 5 carbons could come from the starting alkene. So we have an additional 4. So there is increase by 4. There is increase by 4 carbons. This is a very important observation here of this target molecule. The other observation is the functional groups, as we discussed before. So if you look at this, you will see it's simply an alkane. There is no functional groups present here. This is an alkane. So we need to make an alkane from an alkene. We need to make an alkane from an alkene. This may not be done in one step. It cannot be done in one step. So this has to be done in few steps. Yeah. Okay. Whatever it is, the alkene or any other multiple bonds should be reduced in order to make the corresponding alkane. So we need to make an alkane. So we think of reduction as a possible reaction. Therefore, now this is an alkane with 5 carbons more than the original alkene. We can think of this as coming from the corresponding alkene when there is a double bond between carbon 1 and 2, as in the starting compound. But this would mean an alkene with more carbons. So it's difficult to, well, it may not be difficult, but it can be longer to make an alkene with more carbons from a simple alkene. Yeah? Or we can think of making this alkane from an alkyne now, from an alkyne where there is a triple bond between carbon 1 and 2. And we simply take that transformation from the alkyne with the same number of carbons, obviously, to this alkane by reduction using hydrogenation reaction, uncontrolled. So that's possible, actually. So if we write that down, yeah, okay, then this is the carbon-carbon triple bond. This is what the bond between carbon 1 and 2. And here we have four carbons. So 1, 2, 3, 4, 1, 2, 3, 4. These are 4 carbons, and these carbons that are triply bonded are carbons 1, and 2. And then we will have 3, 4, and 3, 4, and 5. So these are carbons 3, 4, and 5. So we viewed this as a possible step, and it could be a last step, taking an internal alkyne with the same number of carbons to the final target by uncontrolled reduction using hydrogenation reaction. So we say here hydrogen in the presence of palladium on carbon. So hydrogen BDC will take that internal alkyne into the final target alkane. What about this now internal alkyne? How can we make internal alkynes? We learned before that internal alkynes can be made or can be obtained from the corresponding terminal alkynes if the terminal alkyne is deprotonated and the acetylamine is then alkylated. So we can then make this alkyne from internal alkyne from this terminal alkyne. So 1, 2, 3, 4, 5. So again, let's put the numbers just to keep track of carbon. So this is a terminal alkyne. We can make that internal alkyne from it. If we react this first with a suitable base, again, that's already discussed, sodium amide, and now an alkyl halide that has the difference, if you like, of the in number of carbons, so or the increase. 4 carbon, the increase is by 4 carbons, so then we need an alkyl halide with 4 carbons. So here it is, so 1, 2, 3, 4, this time we use Cl. So this is 1-chlorobutane as the source of the butyl group, if you like, or the alkyl group by which the internal alkyne has been elongated as a chain. So this terminal alkyne is then transformed in that into that internal alkynes, in which there is an increase by 4 carbons. So the question now, how can we make this terminal alkyne from this terminal alkene? Can this be done in one step? It cannot be done by one step. So how can we do this? Well, we have to recall the preparation of alkynes. How can alkynes be made? If you remember when we talked about the preparation of alkyl halides, that they can be made from dihalides. Alkynes can be made from dihalides if the dihalide is treated with 2 moles of a base. So if this sort of a dihalide of this type, so say an alkyl halide that has 2 Br groups on between or on the same carbons, of course, which would then be triply bonded, obviously. So between carbons 1 and 2, that's what that means. Yeah. Okay. So 1, 2, 3, 4, 5. So this is the carbon 3, 4, 5. This is the dihalide. If this dihalide is treated with 2 moles of a base, such as sodium amide again, or potassium, 2 moles of potassium hydroxide, the corresponding alkyne will be obtained. 2 moles are needed because this is double dehydrohalogenation. It's a removal of 2 molecules or 2 moles of HX. This is a dihalide now, so maybe it's a little bit more obvious now, yeah? This is a dihalide and that's an alkene. So making dihalides from alkenes can be done in a single step, can be done in one step. And alkenes undergo addition with X2 in order to make the corresponding dihalide. So X2 in this case will be Br2. So this is how this transformation can be achieved in the forward sense. An alkene reacts with bromine to make the dihalide. The dihalide then reacts with 2 moles of a suitable base to make the corresponding terminal alkyne. The terminal alkyne is then deprotonated with sodium amide. The acetylide is then alkylated with an alkyl halide that has the number of carbons by which the target molecule has increased, so 4 carbons. In this case, the internal alkyne is then reduced using hydrogenation reaction to make the corresponding alkane. There is an increase by the number of carbons. The functional group, there's no functional group basically in the target molecule. It is basically an alkane. So this is how this transformation is achieved. using this second example of organic synthesis that can be done with the knowledge of the chemistry of alkynes as a theme.